Scientific realism is a philosophical position asserting that the world described by science is independent of our perceptions and beliefs, and that scientific theories accurately represent that world. This view holds that the entities and processes posited by scientific theories, such as atoms, genes, and gravitational waves, exist and operate regardless of whether they are directly observable. Scientific realism posits that successful scientific theories not only provide useful tools for prediction and explanation but also reveal truths about the underlying structure of reality. The roots of scientific realism can be traced back to the Enlightenment, when philosophers began to emphasize the importance of empirical observation and rational thought in understanding the natural world. Thinkers such as Isaac Newton and later, the development of the scientific method, laid the groundwork for the belief that science can yield objective knowledge about the universe. Scientific realism became particularly prominent in the early 20th century, especially during the logical positivist movement, which sought to establish a framework for meaningful scientific discourse based on empirical verification. Central to the argument for scientific realism is the success of science. Proponents argue that the remarkable predictive power and explanatory scope of scientific theories strongly suggest that they are true or approximately true representations of the world. For example, the success of Newtonian mechanics in predicting the motion of celestial bodies led to the belief that the underlying concepts, such as force and mass, accurately reflect the nature of physical reality. Similarly, the development of quantum mechanics and the theory of relativity has provided profound insights into the workings of the universe, lending further credence to the idea that scientific theories correspond to reality. One key aspect of scientific realism is its commitment to the ontological claims of scientific theories. This entails accepting that the entities described by science, whether they are macroscopic, like planets, or microscopic, like electrons, are real and exist independently of our observations. The realist position contrasts sharply with instrumentalism, which views scientific theories as mere tools for organizing experiences and making predictions, without any commitment to their truth. Instrumentalists argue that the utility of a theory does not necessarily imply that the entities it describes exist, they are simply constructs that help us navigate our experiences. Critics of scientific realism often point to the historical record of science as evidence against the claim that scientific theories accurately represent reality. They argue that many scientific theories once thought to be true have been discarded or replaced by new theories that better explain the phenomena. For example, the transition from phlogiston theory to the modern understanding. Another argument against scientific realism is the pessimistic induction. This position asserts that because many past scientific theories have been shown to be false, it is reasonable to conclude that our current theories may also be false. Proponents of this view argue that just as earlier theories were discarded, so too will today's theories eventually be replaced. This raises fundamental questions about the reliability of scientific knowledge and the extent to which it can be considered true or reflective of reality. Despite these criticisms, scientific realism maintains a robust defense. Realists argue that scientific theories are not static, rather, they evolve and improve over time, often leading to deeper and more accurate understandings of the world. The progression from classical physics to quantum mechanics and relativity, for instance, demonstrates the capacity of science to refine its theories in light of new evidence. Realists contend that this cumulative nature of scientific knowledge strengthens the case for realism, as it suggests a deeper, underlying reality that scientists are gradually uncovering. Moreover, scientific realism can draw support from the predictive success of scientific theories. When theories accurately predict phenomena that have not yet been observed, this serves as an argument for their truth. For example, the prediction of the existence of the Higgs boson based on the Standard Model of particle physics led to its eventual discovery at the Large Hadron Collider. Such instances provide compelling evidence that scientific theories correspond to a reality that exists independent of human perception. Another area where scientific realism finds support is in the field of scientific practice. Scientists operate under the assumption that their theories describe real entities and processes. This practical commitment is evident in the design of experiments, the formulation of hypotheses, and the interpretation of data. The success of experimental science hinges on the belief that the entities being studied, whether they are molecules, cells, or galaxies, are real and can be understood through theoretical frameworks. This conviction underlies the scientific method and is essential for furthering scientific inquiry. Scientific realism offers a compelling framework for understanding the nature of scientific knowledge and its relationship to reality. By asserting that scientific theories provide accurate representations of an objective world, it challenges the notion that science is merely a collection of useful tools. While criticisms regarding the historical record and the problem of underdetermination raise important questions, the success of scientific theories and the practices of scientific inquiry provide strong support for the realist position. As science continues to evolve and deepen our understanding of the universe, the commitment to scientific realism remains a vital aspect of contemporary. The debate surrounding scientific realism is not merely philosophical, it has significant implications for how we understand scientific knowledge, the nature of truth, and the reliability of scientific inquiry. This discourse encompasses various responses to the criticisms of realism, the implications for scientific practice, and the role of scientific realism in addressing contemporary challenges. One important response to the critiques of scientific realism is the development of constructive empiricism, articulated by philosopher Bas van Fraassen. Constructive empiricism maintains that the aim of science is not to find true theories or accurate representations of the world but rather to develop theories that are empirically adequate, meaning they accurately describe observable phenomena. While this position diverges from traditional scientific realism by rejecting the commitment to the truth of unobservable entities, it nonetheless acknowledges the practical success of scientific theories. Proponents argue that as long as a theory can account for observable phenomena, it can be considered successful, regardless of whether it accurately represents the underlying reality. Critics of constructive empiricism argue that it undercuts the scientific endeavor by dismissing the significance of unobservable entities, such as electrons, which play crucial roles in scientific explanations. They contend that a thorough understanding of science requires a commitment to the reality of these entities, as they are integral to the theoretical frameworks that enable scientific advancements. This debate highlights the tension between the practical utility of scientific theories and the philosophical implications of their ontological commitments. Another avenue of defense for scientific realism is the no miracles argument, which posits that the success of science would be miraculous if scientific theories were not at least approximately true. This argument asserts that the ability of scientific theories to predict novel phenomena and to unify disparate observations under coherent frameworks suggests that these theories must reflect some underlying truth about the world. If scientific theories were merely instruments without any truth value, their consistent success would be perplexing, as there would be no reason for them to work as effectively as they do. Moreover, realists often emphasize the explanatory power of scientific theories. Theories that can provide deep explanations for a wide range of phenomena lend credence to their truthfulness. For instance, the theory of evolution not only explains the diversity of life but also integrates findings from genetics, paleontology, and ecology, providing a cohesive understanding of biological processes. This explanatory richness suggests that such theories are not merely useful tools but also reflect fundamental truths about the biological world. The implications of scientific realism extend into the realm of interdisciplinary research. As scientific disciplines increasingly overlap, the realist perspective encourages collaboration across fields, fostering a deeper understanding of complex phenomena. For example, the integration of biology, chemistry, and physics in fields like biochemistry and biophysics reflects a commitment to uncovering the underlying reality of life processes. Scientific realism supports the idea that these diverse disciplines can converge on a unified understanding of nature, reinforcing the belief in a coherent and objective reality. In addition to its philosophical implications, scientific realism plays a crucial role in addressing contemporary global challenges, such as climate change, public health crises, and technological advancements. The realist commitment to an objective reality where scientific findings can inform policy decisions is vital for combating misinformation and fostering informed public discourse. For instance, the scientific understanding of climate change, based on rigorous empirical evidence, underscores the need for collective action to mitigate its effects. A realist perspective encourages policymakers to rely on scientific consensus, promoting decisions that are grounded in empirical reality rather than political or ideological beliefs. Furthermore, the challenges posed by rapid technological advancements, such as artificial intelligence, genetic engineering, and biotechnology, highlight the importance of a realist approach in ethical discussions. As society grapples with the implications of these technologies, scientific realism provides a framework for evaluating their potential consequences based on empirical evidence. This perspective encourages critical reflection on the ethical dimensions of scientific practice, ensuring that decisions are informed by a commitment to understanding the real-world implications of technological innovations. Finally, the role of public engagement in science is essential for fostering a realist understanding of scientific knowledge. As scientific literacy becomes increasingly important in a world filled with competing narratives, the public's ability to critically assess scientific information is paramount. Scientific realism advocates for transparency in the scientific process, encouraging open communication about the methodologies, uncertainties, and implications of scientific research. This engagement not only enhances public understanding but also reinforces the credibility of scientific findings, fostering a culture that values empirical evidence as a basis for decision-making. Scientific realism stands as a robust philosophical position that emphasizes the objective nature of scientific knowledge and its capacity to accurately represent reality. Despite challenges from positions like constructive empiricism and the problem of underdetermination, scientific realism maintains its relevance. In our continued exploration of scientific realism within the domain of philosophy of science, we unravel further layers of complexity that shape our understanding of the nature of scientific knowledge and the pursuit of truth in the scientific realm. By delving deeper into the nuances and implications of scientific realism, we gain a more profound insight into the intricate interplay between theory, evidence, and our quest for a deeper comprehension of the natural world. One of the critical aspects underpinning the discourse on scientific realism is the concept of scientific progress as an iterative process of theory development, empirical validation, and theoretical refinement. This dynamic view of scientific inquiry acknowledges the evolving nature of scientific theories, which are subject to revision, re-evaluation, and replacement in response to new evidence, theoretical insights, and paradigmatic shifts. This perspective underscores the progressive nature of scientific knowledge and the continual quest for a more accurate and comprehensive understanding of the natural world through scientific exploration and discovery. Furthermore, the debate surrounding the realism of unobservable entities posited by scientific theories, such as quarks, gravitational waves, or dark matter, raises profound questions about the ontology of theoretical constructs and their role in explaining observable phenomena. Scientific realists argue that these theoretical entities serve as indispensable explanatory tools that enable us to make sense of empirical data and construct coherent scientific narratives about the underlying structure of reality. This perspective highlights the pragmatic and instrumental value of theoretical entities in advancing scientific understanding and guiding empirical research. Critics of scientific realism challenge the epistemic status of unobservable entities and raise concerns about the underdetermination of theories by evidence, the role of auxiliary assumptions in theory choice, and the provisional nature of scientific knowledge. These critiques prompt reflections on the criteria for theory acceptance, the reliability of scientific inference, and the complexity of confirming the truth of scientific claims in the face of empirical data and theoretical frameworks. By engaging with these philosophical inquiries and debates surrounding scientific realism, we embark on a journey of intellectual exploration that enriches our understanding of the complexities inherent in scientific inquiry, the pursuit of knowledge, and the ongoing quest for truth within the scientific enterprise. Through critical reflection, open dialogue, and a commitment to exploring the intricate connections between theory, evidence, and reality, we deepen our philosophical insights into the nature of scientific knowledge and the enduring dialogue between philosophy and science. As we delve further into the intricate landscape of scientific realism within the philosophy of science, we encounter a rich tapestry of ideas, debates, and philosophical inquiries that illuminate the complexities of scientific knowledge and the pursuit of truth in the scientific endeavor. By exploring the nuances and implications of scientific realism, we deepen our understanding of the dynamic interplay between theory, evidence, and our quest for a deeper comprehension of the natural world. One of the central themes in the discourse on scientific realism is the notion of theory change and scientific revolutions, as famously articulated by Thomas Kuhn in his work, The Structure of Scientific Revolutions. Kuhn's insights into the paradigm shifts that occur in scientific communities highlight the transformative nature of scientific inquiry, where established theories are challenged, revised, or replaced by new frameworks that better account for empirical data and theoretical advancements. This perspective underscores the evolutionary trajectory of scientific progress and the continual refinement of our understanding through critical reflection, experimentation, and theoretical innovation. Moreover, the philosophical implications of scientific realism extend to questions about the nature of scientific explanation, the relationship between theory and observation, and the criteria for theory acceptance within the scientific community. By examining how scientific theories aspire to provide accurate descriptions of the natural world, we confront fundamental inquiries about the reliability of scientific knowledge, the role of evidence in theory confirmation, and the epistemic challenges inherent in verifying the truth of scientific claims. The debate between scientific realists and anti-realists encompasses a diverse array of perspectives on the nature of scientific knowledge, the realism of theoretical entities, and the complexities of theory confirmation in the face of empirical data. While scientific realism champions the pursuit of truth and the correspondence between scientific theories and reality, critics raise valid concerns about the underdetermination of theories by evidence, the role of auxiliary assumptions in theory choice, and the provisional nature of scientific knowledge in an ever-evolving scientific landscape. By engaging with these philosophical inquiries and debates surrounding scientific realism, we embark on a journey of intellectual exploration that deepens our appreciation for the complexities of scientific inquiry, the quest for knowledge, and the enduring pursuit of truth within the scientific enterprise. Through critical reflection, open dialogue, and a commitment to understanding the intricate intersections between theory, evidence, and reality, we enrich our philosophical insights into the nature of scientific knowledge and the ongoing dialogue between philosophy and science. In our continued exploration of scientific realism within the realm of philosophy of science, we delve deeper into the intricate web of concepts and debates that shape our understanding of the relationship between scientific theories and the external world. By delving into the nuances and implications of scientific realism, we gain a more profound insight into the complexities of scientific knowledge and the pursuit of truth in the scientific enterprise. One of the key aspects of scientific realism is its emphasis on the notion of scientific progress as a cumulative and evolving process of theory development and empirical validation. This perspective acknowledges the dynamic nature of scientific inquiry, where theories are refined, revised, and sometimes replaced in light of new evidence and theoretical advancements. The iterative nature of scientific progress underscores the commitment of scientists to uncovering the underlying truths about the natural world and expanding our knowledge through continuous exploration and discovery. Moreover, the debate surrounding the realism of unobservable entities postulated by scientific theories, such as subatomic particles, black holes, or genes, raises profound questions about the nature of scientific knowledge and the limits of empirical observation. Scientific realists contend that these theoretical entities, despite being unobservable directly, are indispensable for explaining and predicting observable phenomena, thereby underscoring their ontological status within the framework of scientific realism. Critics of scientific realism, on the other hand, question the epistemic justification for positing the existence of unobservable entities and underscore the challenges of confirming the truth of scientific theories beyond their empirical success. This skepticism prompts reflections on the nature of scientific inference, the role of theoretical frameworks in guiding scientific research, and the complexities of theory confirmation in the face of underdetermination by evidence. Furthermore, the interplay between social, historical, and cultural factors in shaping scientific knowledge adds another layer of complexity to the debate between scientific realists and anti-realists. Understanding how scientific theories are influenced by broader societal contexts, scientific paradigms, and disciplinary norms enriches our appreciation for the multifaceted nature of scientific inquiry and the diverse perspectives that inform our interpretations of scientific theories and their correspondence to reality. In essence, the ongoing dialogue between scientific realism and its critics underscores the rich tapestry of ideas and perspectives that shape our understanding of the nature of scientific knowledge, the pursuit of truth in science, and the complex relationship between scientific theories and the external world. By engaging with these debates and reflecting on the implications of scientific realism, scientific realism, as a philosophical stance, delves into the nature of scientific knowledge and the relationship between scientific theories and the external world. Building upon the foundation laid in the previous discussion, we will further explore the nuances and implications of scientific realism in the realm of philosophy of science. Central to the discourse on scientific realism is the notion of the no miracles argument, which posits that the empirical success of scientific theories, such as their ability to predict and explain natural phenomena, suggests a deep connection between these theories and the underlying structure of reality. This argument asserts that the remarkable efficacy of scientific theories in making accurate predictions cannot be mere coincidence or luck. Rather, it points to the inherent truthfulness of these theories about the world they seek to describe. Moreover, scientific realism emphasizes the progressive nature of scientific inquiry, whereby scientific theories evolve over time through a process of hypothesis testing, experimentation, and refinement. This iterative process of theory development and empirical validation underscores the commitment of scientists to uncovering the fundamental truths about the natural world and revising our understanding in light of new evidence. Critics of scientific realism raise concerns about the underdetermination of theories by evidence, highlighting the challenge of conclusively establishing the truth of a scientific theory based solely on empirical data. This epistemic limitation underscores the complexity of theory choice and the provisional nature of scientific knowledge, prompting discussions about the criteria for theory confirmation and the role of auxiliary assumptions in supporting scientific theories. Furthermore, the debate between scientific realists and anti-realists extends to questions about the nature of scientific progress, the realism of unobservable entities postulated by scientific theories, and the role of social, historical, and cultural factors in shaping scientific knowledge. These discussions enrich our understanding of the multifaceted nature of scientific inquiry and the philosophical underpinnings that guide our interpretations of scientific theories and their relationship to reality. In essence, the exploration of scientific realism invites us to contemplate the intricate interplay between scientific theories, empirical evidence, and the quest for knowledge about the natural world. By engaging with questions about the nature of scientific truth, the reliability of scientific theories, and the epistemic challenges facing scientific inquiry, we deepen our appreciation for the complexities inherent in the pursuit of understanding and the ongoing dialogue between philosophy and science. Scientific realism is a philosophical position that asserts the existence of an objective reality independent of our perceptions and theories, and it holds that scientific theories aim to provide true descriptions of this reality. In essence, scientific realism posits that the scientific endeavor is a genuine pursuit of understanding the world as it truly is, rather than merely a convenient tool for prediction and manipulation. At the core of scientific realism lies the belief that our scientific theories, despite being provisional and subject to revision, accurately represent the underlying structure of the natural world. This view contrasts with instrumentalism, which posits that scientific theories are merely useful tools for making predictions and organizing empirical data, without necessarily reflecting an objective reality. Proponents of scientific realism argue that the success of science in explaining and predicting natural phenomena provides strong evidence for the approximate truth of scientific theories. They point to the empirical success of theories such as Newtonian mechanics, quantum theory, and evolutionary biology as proof of the correspondence between scientific theories and the real world. Moreover, scientific realism emphasizes the role of observation and experimentation in validating scientific theories and hypotheses. By grounding scientific claims in empirical evidence and subjecting them to rigorous testing, scientists aim to uncover the underlying truths about the natural world and refine our understanding of reality. One of the key challenges facing scientific realism is the underdetermination problem, which highlights the fact that multiple theories can account for the same set of observations. This suggests that empirical success alone may not be sufficient to establish the truth of a scientific theory, leading to debates about the criteria for theory choice and confirmation. Despite these challenges, scientific realism continues to be a dominant and influential perspective in the philosophy of science. It provides a framework for understanding the nature of scientific knowledge, the relationship between theory and observation, and the pursuit of truth within the scientific enterprise. In conclusion, scientific realism asserts that scientific theories aim to provide true descriptions of an objective reality independent of our perceptions and theories. By emphasizing the empirical success of scientific theories, the role of observation and experimentation, and the quest for understanding the natural world as it truly is, scientific realism offers a compelling perspective on the nature of scientific knowledge and the pursuit of truth in science.